Hello everyone, I'm Wang. I'm very glad to have this opportunity to attend the conference. The topic of my presentation is Research on Indoor Passive Location based on LoRa Fingerprint. I'd like to divide my presentation into four parts: background, approach, experiment, and conclusion. Firstly, I would like to introduce the background of our research. According to whether the positioning target needs to carry positioning equipment, indoor positioning can be divided into active positioning and passive positioning. But whether it is active positioning or passive positioning, it includes two stages: offline data acquisition and online target positioning. In the offline stage, we must first use related equipment for data collection, and then use appropriate filtering algorithms to process the data, and then use machine learning algorithms to train the data model to generate a fingerprint library. In the online positioning phase, we compare the data collected in real time with the data in the fingerprint database, and finally, get the location information of the target. Active positioning collects data from mobile devices at different locations, then process and analyze the collected data, and finally predict the location based on the trained data model. This method requires the target to be positioned to carry the positioning device at all times, but it's difficult to achieve in some special situations. For example, when you want to locate a person who broke into a certain area illegally, it is impossible for him to take the initiative to carry a positioning device. In the case of passive positioning, the target don't need to carry a positioning device, as mentioned above, which is also unsatisfactory in some cases. In our experiment, we use LoRa-related equipment. LoRa means long range. This equipment not only has a long transmission distance, but also can work for a long time with power consumption. And it is widely used in the field of Internet of Things. Before our experiment starts, we need to fix the transmitter and the receiver at a certain position in advance. Firstly, collect data in the offline stage for processing and model training. Then, in the online phase, if a target enters the detection area, according to the influence of the object on the signal propagation path in the area, then compare the collected signal strength value information of each LoRa node with the data in the fingerprint database, and then the location information of the target is determined. Next, I briefly introduce the system architecture of our research. The system is mainly composed of LoRa gateway, LoRa node, and the network server. Firstly, it is necessary to establish the communication between the LoRa nodes and the LoRa gateway. The LoRa node will send an uplink signal frame to the LoRa gateway, and then the LoRa gateway will calculate the signal strength value of the LoRa node at this time based on this signal frame. And the LoRa gateway will also send a confirmation signal frame to the LoRa node, but which is not necessary. After the LoRa gateway obtains the signal strength of the LoRa nodes, it will send the data to a network server. The signal frame structure sent by it is shown in the figure, where index is the unique ID of the signal strength value of the LoRa node at a certain moment. ID is assigned to identify LoRa nodes. Time is the time when the signal strength value of the LoRa node is obtained, and RSSI is the signal strength value representation of LoRa nodes. After the network server receives the data, it will save the data to the fingerprint database for further processing. Then I will introduce our experiment. The five-pointed star is the LoRa gateway, the triangle is the LoRa nodes, and the numbered circle is the location where the data is collected. We are experimenting in a rectangular indoor area, and the distance between points is 3 meters. Firstly, collect the data of each node when there is no target in the experimental area, and then let the positioning target exist at each point for a period of time. The collected data is divided into a training data set and a test data set. We first use the difference limiting filtering algorithm to filter the data so that noise data can be removed and the overall characteristics of the data can be preserved. These two pictures are the signal strength distribution diagrams of the 3 LoRa nodes when the target exists at each point in the area. The different colors represent different LoRa node devices. It can be seen that the signal strength value distribution of the 3 LoRa nodes at each point is hierarchical. It also can be seen that the distribution of the signal strength value of each LoRa node at each location is hierarchical, and the hierarchical distribution at all locations has its own unique regularity. We judge the position of the target in the positioning area based on the difference in the distribution of signal strength values of different LoRa nodes. In addition to using the difference limiting filter algorithm to remove the noise data, we also use the Gaussian MB algorithm for model training on the filtered data. Finally, take a look at the analysis and conclusion of the results. Our research uses long-distance, low-power LoRa technology to build an indoor passive positioning system based on LoRa single fingerprints and collect data in a rectangular indoor area using difference limiting filtering algorithm and Gaussian B algorithm to filter the data and model training respectively. First of all, our training data set. Our training data set contains different numbers of data, especially position 0 is the state when no target exists in the positioning area. It can be found that the closer to the LoRa gateway, the higher the accuracy. And when the positioning target is on the straight line between the LoRa gateway and the LoRa node. Since the target has a great impact on signal propagation, its changing low is more obvious, and its accuracy rate is also here. Secondly, we also compared the results of our algorithm and the SVM. The highest accuracy rate of the SVM is only 84%, and the accuracy rate at other points is lower. But the accuracy of our algorithm at each location is about 96%. Next, I will introduce the applications and some shortcomings of our research. It can be used to monitor certain areas in large museums or prisons, because in these special circumstances, it is impossible for the person to be located to actively carry the positioning device. Therefore, we can only use passive positioning instead of active positioning to monitor these areas. The equipment used in our solution has a long single transmission distance, so the location area that can be covered is large. Not only that, our experiment had a extremely low power consumption, and a battery can support its work for several years, which has strong practicability. But there are also some problems that we need to further study next. For example, this method can only detect a single target and cannot accurately detect multiple targets that appear in the positioning area at the same time. The current result of our experiment is that when the positioning accuracy is 3 meters, the average accuracy rate is about 96%. Our next goal is to improve the positioning accuracy while maintaining a high accuracy rate. That's all for my presentation. If you have any question, please feel free to contact me. Here is my email address. That's all. Thank you.